about the extended UTXO model on Monday, although it was some practical as well. I mean, we did send some money on Cardano back and forth. Now we want to write our first smart contract, and Robertino kindly agreed to do that part. So the floor is yours, Robertino.
Thank you so much, Lars. Yeah, so as today we're going to write our first smart contracts, and we will also deploy, actually run them in the blockchain. And I would like to make it as interactive as possible. So if you go to our repository, you will see that there's a new folder called examples Aiken. So if you pull these changes and you see into it, you will see that to configure the container, you can check this is on your host machine, or I mean on your shell, in the terminal in your computer without Docker running. You can run this to check the group that you belong and the ID of the user. And then you have to create a .env file that is inside the dev container. So let me share with you. You can all see my VS Code.
I can.
Okay.
Yes, I can.
Awesome. So I think it's soon enough. So if we go to the dev container, you have to create this .env file, and inside its .env file, you will see you'll have to create these environment variables, one called maestro_token, and this you have to put your own. That we'll see now how you can do that. And here you have to create the user ID and the group ID with the values that you got running these two commands in your terminal. So to get this maestro token, you have to go to CoMaestro, which is an infrastructure company that provides a bunch of really cool services for you guys to build without needing to run all the infrastructure yourself. The one thing that we really care about now is that they run their own nodes, so we can just use the API, their API. So if we log in, we have to log in again. If you log in, you won't have anything here. So you have to go to the dashboard, create a new project. And as soon as you create the new project, you have to choose the network. In this case, I choose preview, but you can choose pre-prod. This doesn't change much. And here you will have this, you will get a prompt. Actually, I'm going to rotate the key, or reset. Yes, I want to reset, and you'll see you successfully rotated the API key. So you will get this API key, and you have to copy it. And this is what we're going to use right here. And that's it. So once you have that, both, let me know if anyone is struggling with at any point in time. Once you have that, you have to actually rebuild the container. Or if you haven't opened VS Code yet, you can just create this file and then open VS Code, and it will prompt you to use to open the container, and that's it. Then you will have the development environment ready. It will take a bit, not much. Let me know if anyone has questions, but if that's out of the way, I would like to get started.
Just want to mention this Maestro token. I think they have a free tier, right? so you don't have
Yes.
to pay anything.
Exactly. Yes, I'm using the free tier. So as you can see, and I just use 1% doing all the testing for this lesson. So it's more than enough to, if you're not building for production, more than enough to play around. And also like a different way of having the a development environment without running it in your own computer is to use Demeter Run. Demeter.run. You create like an account, and you will be prompted like to get one of their getting started repos, or you can use your own repo, which is the one that we are using right now. So if your computer for some reason cannot run the Docker image, which is fairly light, but still it's still a process on top of your normal processes. So if that's too much for your computer, you can use something like Demeter, and you can run it in your browser. I won't go over all that because you can do it while doing the homework. But if you excuse me 1 second, I'm going to switch to the slides. So
It was at least 10 seconds.
sorry. Share screen again. Okay, so let's do a quick overview. So everything is up to speed with what we're going to talk about. We're going to do a short overview. If you know other programming languages, which you already know Haskell, I mean, or you already have basic knowledge of Haskell by now. And if you already knew any other languages, this will be a helpful overview to get you, to give you a quick mental model of what you can and you cannot do with Aiken. So details to keep in mind before we get started. Aiken is meant to be a language that only build validators, to only build smart contracts, nothing else. So it's constrained by Cardano's virtual machine and what a validator can and cannot do. So we have to know a few details about that. The first one is that Cardano smart contracts are validators. They are called validators. They either validate or reject transactions. So they don't do other stuff. A validator cannot by itself start a process or create a transaction. The validator, the only thing it does is to accept or reject transactions. Then we need to have both on-chain code, which are the validators, and off-chain code it's used to query the blockchain, create transactions, and everything else that is not validating the transaction. We need both the on-chain and off-chain to have a complete dApp. If you only have the validators, they don't do anything. They're just there, stateless. So you need to have off-chain code to interact with them. The on-chain code part contains the core logic of your dApp and the code that can be exploited to steal assets. So that's the main reason you have to be extremely careful with it. The off-chain code has to be, of course, properly written. But if you mess up something in the off-chain code, and your on-chain code is properly written, nothing extremely bad could happen to the funds locked by the validator. Nothing could happen to the funds locked by the validator. So you have to be extremely careful when writing on-chain code, but you can be just regularly careful writing off-chain code, like same as servers and websites. The address, the fourth point, the address of the validator is a hash, like Lars explained before, derived from the validator's logic. So you cannot change a validator that already logs some assets after the fact. This means that if you logged some assets using a validator and then you realize that that validator is wrong for some reason, it's exploitable, or you cannot unlock the assets or whatever, you're done. You cannot change it. Like, that's it. Once it's deployed, that's it. Because if you change the logic of your validator, it's going to have a different address, and that new address is not the one locking the funds that you already locked with the original validator. So it's really important to have everything properly tested and reviewed before locking real-world assets. Another thing, the fifth point, is that we can use a single language or different language for the on-chain and off-chain code. We used to use Haskell for both up until recently, and plenty of companies still do. But today we have more options, and in our case, we're going to cover Aiken for on-chain code, and we're going to, in this lesson at least, use TypeScript for the off-chain code. We may change the off-chain code at some point for to use Haskell or whatever you want to use. And finally, independently of the language you choose to write your validators, as I just said, you can write in Haskell, which is called Plutus TX. Or you can use Aiken, and there are others. But no matter the language the developer writes the validators with, it has to be eventually compiled to Plutus Core to run on the blockchain. So the Cardano blockchain has the Plutus virtual machine, which is the virtual machine that interprets the code, and that means that it can only understand Plutus Core. Every other language is just the language that the developer uses, but not that the machine uses to interpret it. So at the end of the day, once you have the smart contracts that you like, you have to compile it to Plutus Core. We're going to do this today. It's really easy, actually. So let's start with Aiken. Language highlights. We already saw Haskell, so there are a few things the Haskell that we have here, but we don't, but others that we don't. So to get started, as I said before, Aiken is only for on-chain. It's not an embedded domain-specific language. It's like its own standalone language that can only be used to write on-chain. It's purely functional-ish. I mean, it's the underlying machine interprets Plutus Core. So at the end, you are constrained by the Plutus virtual machine. And when we write a code, there are virtually no side effects that you can produce using Aiken, except for the side effect of failing earlier, at least for the user of the Aiken language. There are a few things that you can do to produce the side effect of failing earlier. And that's pretty much it. You cannot read or write files. You cannot connect to the internet. That's it. And it has a statically type with inference. The inference works pretty much all the time. So if you are getting the wrong type for some reason, it's likely that you did something wrong. But it's nice, so it's statically typed. We can choose to write the types or not. It's usually a good idea to write the types just for documentation sake, because it's easier to read the code. Aiken doesn't have higher candidate types or type classes, but it does have some really goodies like first class functions, custom types, recursion, modules, generics, and a lot more. Pattern matching, for example, that's really cool. The type system, if you know other languages to write, if you know other languages to write Pluto smart contracts, this is not your first time. The type system is not as expressive as Plutus TX and Plutarch, but it's good enough for 99% of the cases. If you don't know, and this is the first time you heard about Plutus, don't worry. One thing that you should understand is that it has a standard library, same as Haskell, has a standard library, and it has its own compiler written in Rust. All we need to actually go from Aiken to the Bluetooth core is just this compiler, and that's it. We don't need anything else. If anyone has questions, just speak up. Now, tooling. This is just like 5 slides, and then we're going to go. Tooling highlights. Aiken has great documentation. And on top of that, we have a tooling manager called AkeUp. It's similar to JCUp. If you have used it, you may have used it if you install Haskell by yourself. You haven't if you use our development environments. But the thing is that you just have to run that to install different versions of Aiken and in other tooling related to Aiken. The bigger and more important part of our tooling is the Aiken CLI. It's like an only one CLI that does everything we need. At the project level, this Aiken CLI can create, format, type check, and build projects. It can also manage dependencies, so other people can create their own libraries, and we can import them. We can import the libraries. We can also generate documentation, and we're going to see that how. And blueprints, which are description, interfaces, descriptions of the interface of our smart contracts. At the validator level, it can compute the validator addresses, as we're going to see now that to interact with validators, we need the address because we need to find them. And it can also run tests. It has an integrated test suite. And actually, this last week, they added property-based testing. That is, I believe, is not on the release version, but it's already available on beta or alpha. So it has property-based testing, if you know what that means. Else, if you don't know what it means that, I mean, are we already covered testing?
We did have it. Yeah, quick check.
Yes.
So they better know what it means.
Oh, yes. Yes, you're right. So it has property-based testing. So everything Lars explained, except shrinking, because I think they don't have shrinking, or they have some weird implementation, applies. On top of that, we can simulate transactions, and we can work with untyped Bluetooth core, which is like the last representation of our smart contract that the machine actually understands, the virtual machine actually understands. And on top of that, we have an LSP and integration with VS Code, Vim, and Emacs, etc. So we have pretty much everything we need. I don't think you need much more to work with that. If you have worked with pretty much any mainstream language, you expect to have an LSP, a proper CLI, etc., integration with your favorite text editor. You have all that. So let's do the demo. From now on, it's going to be code, constant code. So make sure to stop me if you don't understand something, because I never did like a 3-hour lecture on Aiken. What I'm going to do is to start with a very low complexity, and then we're going to write a simple validator. We're going to write the off-chain code to lock the ADA and the validator, and then we're going to write the off-chain code to release the ADA from the validator, and we're going to keep doing that recursively until we have a time overflow, and we need to stop. So let's see if anyone has any questions.
No, in the chat.
Perfect. Thank you, Karina. So let's actually, before that, let's see. So, no, one sec. For some reason, the Zoom stopped working. Why now? I have no idea.
Oh.
No. Well, I cannot Zoom, so I hope. Yes, I Zoom before the lecture. Amazing. So, I wanted to show you how to create from scratch. Actually, I can show you inside here. So, no. So, we have an empty folder, and we have the Aiken CLI. If we run Aiken, let me close this. If we run Aiken, we see that we have a bunch of really useful commands. We can create new Aiken projects, format, build, compute validator's address, checks, add dependencies, generate the docs, etc. In our case, we already have the project created, and actually we added more stuff on top of the default. So I wanted to show you how you can start from scratch. So imagine you are in your own computer and you already installed Aiken. You can install Aiken. If you go to aikenlang.org, now it works. If you go to aikenlang.org and you click on Get Started, you can run these commands to get started, and then like install Aiken or ACAP. Actually, if you run this, you will get ACAP, and then you run ACAP that is going to install Aiken. So if you do that in your own machine, then you can run Aiken like I just did and create a new project like this. So Aiken new, and if you run it like this, it's going to give you an error that we need a name. So Aiken new, project. And if you do that, it's going to give you it's going to nag you, but in a nice way, because as you can see, we have a really nice error messages. It's going to tell you, hey, the name fake project is not a valid name because it must have the pattern of owner/project. It doesn't say here, but this is because the owner, you have, or you could put your GitHub handle, so then it's already set up to work GitHub or Bitbucket or whatever, and it's going to do the setup. I'm going to show you right now, so it's better to show than tell. So a new, and when we say fake project, there you go. So we successfully create our fake project. Fake project. Do we have 3 inside? No, we don't have 3. So this fake project has 3 libraries, but we can see it right here. We have the delete me folder, fake project. So this is a brand new Aiken project with a README. So let's start from bottom to top. So the README gives you some really simple explanations that you can check later. It's super short. The important part is here we have the aiken.toml file. So this file is sort of the equivalent of the Cabal file that we use so far. So here we have some general descriptions of the project. And then here's what I said before, that you can, if you put as owner your GitHub handle, it creates this repository description that the user is the owner and the project is fake project, and the platform chooses GitHub as default, but you can change this, of course. And then as dependencies, we have the standard library. So we're going to see like what contains the standard library later. So we're going to ignore the build, the docs, and the artifacts. As validators, we get an empty validator. But here we have to add our own validators. And as library, we have the fake project library. So here you can write code to reuse inside your validators. And that's it. Like that's really a small and simple setup. We added on top of that, we added a few more stuff. So we need the dev container because we don't want to force you to install by hand everything. So we have the dev container. We added the assets folder. We're going to save here our keys, the keys of Bob and Alice, and we added the off-chain folder that we pre-populated with a bunch of scripts, TypeScript scripts, and the validators. I already created a few, but they are empty because we have to do them. The off-chain code, of course, we can write from scratch, but it's more code. And I think if I write this from scratch, we are just going to do the super basic gift and born validators, and we're not going to reach more interesting ones. So I just pre-written, and we can go over the code later. So this is what we have so far. So let's write some code. Aiken has very few built-in types. There's just 6, I think. But I mean, we could go over everything one by one, but you have already a really nice documentation for that. Actually, if we go to the documentation, you can see like you can do a language store, like primitive types, variables, constant functions, custom types. So because you already can do that, I'm not going to repeat the documentation and just going to start coding. So the first thing we need to do is to create a function. As we said before, the Plutus validators are just functions, pure functions that return true or false. True if the transaction that I want to use the validator with, it can be performed, and false if it cannot. So to create a function we have a question there, or?
No, someone joined the meeting.
So if we have a function, if we need a function, we can create with the fn keyword. And then we have to name the function. We can name the function whatever we want. We are going to create right now, the first validator is going to be a validator that always returns true. So it just gives the money that is locked on it to everyone that asks. So we're going to call the validator gift, and we have to pass the parameters. I'm going to shut down GitHub Copilot, disable operations. Perfect. So we have the give function. We in this case, we don't use spaces. We use, like in Haskell, we use parentheses for the arguments and square brackets for the body of the function. And now, all validators, as Lars already said, take at least the datum and a script context, and some of them take as well, a redeemer and a script context, some of them take datum. So in our case, we're going to lock some ADA in the gift validator. And this type of validator is called a spend validator because it chooses, it allows you or it blocks you from spending the assets that are locked by the validator. And for that, we have to provide a datum, a redeemer, and a script context. So we can use named parameters. So we can use datum, we can use redeemer, and we can use script context. And now here we can, for example, run a what to do. And we get a bunch of warnings. This is the explanation, no big deal, but unfound unused private function gift. And maybe you want to enforce some side effects, blah, blah, blah. The thing is that we are not using the gift function. So the datum, redeemer, and context. So we're going to ignore them using the underscore. And because it's a validator, we want it to be a validator. It has to return Boolean. So we can indicate that in the type, if we use arrow bool, this, if you use Rust or TypeScript, this looks kind of familiar. So we have the gift function that takes a datum, a redeemer in the context, and returns a Boolean and doesn't do anything. So we said that we want to always approve the transaction. So it has to return always true. So what can I do to return always true? Well, I just return true, ignoring pretty much everything else. So this function takes 3 parameters, and returns true, always, independent of the parameters. This is what we want in our transaction. We want a validator that only returns, that always accepts the transaction. It always allows you to unlock the funds. The thing is, this is not a validator. This is just a function. It doesn't have side effects because this is just a function. So how can we transform this function into a validator? Well, all we need to do is to use the validator keyword. Actually, I have a snippet, but I'm not going to use it right now. Validator. And inside the body, we're going to put this function. And there you go. Now we promoted the gift function that used to be a regular pure function into a validator. Now it can be compiled to Putoscore and run in the blockchain as its own validator. If you, for some reason, we have really nice errors here. So if you, for some reason, write something like miss something, you will get an error saying, hey, validators require at least 2 arguments and at most 3 arguments. We're going to see why at least 2 arguments in a future lesson, but in this lesson, we're going to use 3 arguments always. So we have our validator. Now, how can we use it? How can we actually run it? So as you can see, the code is really simple for the on-chain code, but the off-chain code is a bit more convoluted. We're going to use Lucid for the off-chain code. And the first thing we're going to do is to create an instance of Lucid. In our case, let me open the Lucid documentation. So here we have Lucid. Lucid is a TypeScript library that handles the creation of transactions. And we can also query the blockchain and create keys, etc. So the point is that you can use a TypeScript to create to write the off-chain code, and this is what we're going to do right now. In our case, the first thing we need to do is to create the instance of Lucid. Lucid has to interact with the blockchain, but it's just a library. It needs a provider. It needs some way to interact with the blockchain. And for that, we're going to use the Maestro provider.
I may just interrupt briefly. I just wanted to say that Lucid is in principle like the Cardano CLI we saw last time, but on a much higher level. So in principle, you could write your off-chain. I mean, you could interact with your new smart contract using the Cardano CLI, right? But that would be very painful. As we saw last time, it's quite tedious to interact with the blockchain with the Cardano CLI. So Lucid, in principle, has more or less the same functionality, but on a much higher level. So it's much nicer and more comfortable. It's nicer and easier, and it's TypeScript. So you don't have to write bash scripts. You can use a nicer language.
Exactly. And we're going to see now when we generate the keys and when we actually interact that there's a bunch of things that we don't have to take into account because Lucid just does it for us. So that's amazing. So we start by getting our token from the end file for the environment. Then we create a new Maestro object that because we're using Maestro as a provider, and we choose the network preview. We provide the APK we just read, and Maestro has this functionality called Turbo Submit, but it's only available in the paid plan, so just put false here.
If I can just interrupt one more time,
Yeah.
in this line 3, to read the environment variable, there's this Dino. So we are using, I mean, as you said, it's Lucid is TypeScript. So in particular, you could also use it from the browser. So if you write a DApp, you can write a DApp that's basically completely in the browser. So you can use Lucid and TypeScript to, from the browser, interact with the blockchain and interact with your DApp. But we are not doing that in this example. So this is not in the browser, it's run locally. And there are different ways to do TypeScript locally. I think the classical way is Node.js, but we are using Dino. So Dino is a more modern runner for TypeScript. And that's also contained in this dev container, so you don't have to install it. So this is like Dino specific, how to read the environment variable. Obviously, if you were in a browser, you would need a different way to get your Maestro token into context. Yeah, just saying. So we use Dino to run, to later execute our TypeScript code.
Exactly. So all these scripts that we have here, you could, if you wanted, just deploy them in the backend and then provide APIs for your front end website, or you can just avoid relying on these things that are specific to Dino. Because, like, for example, in the web browser, you cannot read and write files, and we're going to do that quite a lot. So you can avoid relying on things that depend on the backend and just run your off-chain in your front end. And you can do that. So actually, we have an example of that, but maybe at the end we're going to share a full-on app if we make it on time. So okay, so as Lars said, we're running this in the backend. We have our Maestro token, and then we just create a new Lucid instance and export it. So from now on, every time that I'm going to use this Lucid instance, it's going to be this one that is already initialized with the correct values, etc. So we want to send money now to the gift validator. We need first, I mean, the validators only block money from being consumed from the validator. So every time we send, we create a transaction in Cardano or in Bitcoin, for what it's worth. We consume UTXOs and we create in some place, and we create UTXOs somewhere else. So validators only care about the consuming part. So anyone can create UTXOs in a validator, but only authorized ones can actually consume them from the validator. So what we need to do now is to send money to the validator. And I create the script to do just that. Locked ADA in gift or burn validators. So in this script, let's go step by step. So in this script, first, of course, we need to read the text. We need to read Alice Pokey hash, and we don't have an Alice Pokey hash. So we have to generate wallets. We don't have wallets here. Of course, if you run this on the front end, there's a super easy way to prompt the user to sign the transaction with their wallet that they have installed in the browser. But because here we're running in the backend, I have to just generate the keys. And as you can see, all I need to do is to run this generate private key function to generate Alice public key and Bob public key. And then I'm going to write these public key hashes, these public keys into the assets folder called Alice public key and Bob public key. So we already did this with the Cardano CLI the other day. And because it's a bit cumbersome to write like Dino run, allow, we have to allow to write files, allow to access the, we have to allow a bunch of stuff because Dino is super secure and it's everything is opt-in. And because that's a bit cumbersome, I added an alias that is called it's called run script. And it does Dino run, allow read, allow write, allow net, and allow env to be able to read from the environment. And from then on, I can do whatever I want. So I'm going to run the script that is inside the off-chain folder. And as we see on top here, generate Alice and Bob. And if I run this, the Alice private key saved and Bob private key saved on assets. So let's go to assets. And there you go. We have the private keys of both Alice and Bob. So what we want to do is that Alice is going to lock the ADA in the validator and Bob is going to unlock it. And if we go to off-chain, we can actually check their wallets. I wrote a script for that as well. So as you can see, we're doing the same stuff we did with the Cardano CLI, but now with Lucid. So we want to check what UTXOs are inside the wallets. So we're going to do this twice, both first for Alice and then for Bob. And we're going to just read the private key. We're going to select a wallet from private key. So we're going to tell the Lucid instance, now you are using the wallet derived from this private key. And then once we do that, we're going to print the address of the wallet. We're going to print the UTXOs. As you can see, we have here a lucid.wallet.address, lucid.wallet.get UTXO. This already comes in Lucid pre-built. So we're going to print this to the console to see what it has, and we're going to do the same with Bob. So let's do that. Let's run script off-chain check wallets. So we have Alice address and it has no UTXO because I just created it. And we have Bob address that also has no UTXOs. So we can do the same as Lars did the last lesson. We can just take this address and ask the faucet to send us some money. But I think it's going to be faster if I just send the money myself. So I'm going to send 1,000 ADA to Alice. And now all we have to do is wait for a bit. Oh, it's already there. Awesome. Instant. So now Alice has a UTXO in her wallet that contain, we have the transaction hash, the hash, we have the index, and that contains 1,000 ADA, but in loveless, of course. So you have to add 6 zeros. And so there you go. Alice already has money, so she can start doing transactions. Let's, not sure what it changed, but yeah, sure, save. Now, Alice needs to create a transaction to send money to the validator. But the thing is, this validator is just Aken code. I mean, and we need the actual code, and we need the address to know where to send the money. So once you have a validator that you are happy with or that you want to test, you can just run Aken build. And if you see right here, we don't have any JSON file, but if we run Aken build, now we have a Bluetooth.json file. And if we go in, we'll see that this is like a blueprint of our project. So we have this preamble that just has the title, description. It has, very important, the version of the compiler. It has the Bluetooth version and the license. And right here, we have.
Wait.
Yeah.
Sorry, Robertino, we have a question. Adrian, go ahead.
Yes, I just got an error because I had I cannot read a property in mean phi coefficient or something like that. I don't know if you can.
Yes, so I know what happened. So have you set up the .m file inside the dev container? That temp, this one.
Yes, but yes, I already put the Maestro token.
Okay, so try to rebuild the container. If you can run rebuild container like this. So the thing is that it's likely that it hasn't picked up the Maestro token yet, and you can actually double check if you do the console log. If you do like this, it's likely you have like an empty. Can you check?
Okay, let me check. But
sure.
I think that I am done. Okay.
No problem.
Yes. Thank you.
So let me know if you're still struggling rebuilding the. Yeah, I think if you have the token and you just rebuild, it should work. So in these blueprints, in the Bluetooth.json, we have a list of validators because we can have a bunch of validators. There's no need to have just a single one. And usually you have more than one for non-trivial dApps. So we have the validator and we have the title. The title is just the name of the file dot the name of the function. In our case, we have the GIF born 42, and the function is called GIF. So that's how it's called right here. We have the datum. The datum is just that, as it's called underscore datum because we call it underscore datum right here, and it already knows that the type, this schema is going to give us the type that is this is a reference for something in the bottom that is called data, and the description is that this data type that we haven't talked about yet. It represents any Bluetooth data. So I think it might be a good idea to... No, let's finish this, and then we're going to explore the data types. But as you can see, this is the data. This data type, it represents like any possible Bluetooth data, and this is what we have as datum and as redeemer. As you can see, we have this. The redeemer can be anything. I'm not constraining the type or the value in any way because I'm not using it. And finally, we have compile code and hash. What it interprets by the virtual machine, what it really matters to the blockchain is this set of bytes. This set of bytes is the actual smart contract that you run in the blockchain. The more complicated, the larger. And this is what we actually want this is what we need to calculate the address. So if we go to what we wanted to do at first, let's split this. If we go to logged ADA in gift, let's see this. So we load Alice wallet. We read the file, load Alice. We select the wallet with Lucid. We load the validator. This validator is this file. So we read the file Bluetooth.json, and we parse this JSON. And then we haven't seen the burn yet. And then we create this spending validator. This spending validator needs to contain two properties. The type of the validator, it can be Bluetooth V1 or V2 in this case. It could also be a native token, but I think it's not supported by Lucid. So we indicate that this is a Bluetooth V2.
Actually, Lucid does support native.
Nice.
Well, yes.
Awesome. So we could use native as well. Actually, can we maybe if I do it like this? Yes.
Right.
Awesome. You are right, Lars. Of course. So we have native Bluetooth V1 and Bluetooth V2. In our case, we're using Bluetooth V2. Bluetooth V3 is already in the way. So likely in a very short time, you will have the third option, Bluetooth V3. And then we need the actual script. So if you're actually deploying this like a production-ready app, this script is going to be likely hard-coded, not like dynamically load from a file that can change at any time. But because we are just testing things around here and we want to iterate quickly, what we're going to do is just go to the Bluetooth JSON, and inside, this is our file. Inside Bluetooth JSON, there's the validators list, as you can see here. And then inside the validators, we're going to filter the validators that had the title equal to gift born 42 gift, which is this one. So after that, we have just only one. So we're going to have a list of only one validator. That is the one that we care about. So we're going to select the only element from the list, and we're going to access the compile code that is right here. So after all that, we just got this compile code that you could arguably just copy and paste here, and that's it. So this is what I want to show you right there, just to make sure that I don't lose you with the reading the stuff. We have an error because we're not using the gift validator, but we're going to use it right here. So we have a wallet with Alice credential, and we have our gift validator. Now, I just rename it to validator because to avoid changing this when we work with the burn validator. So just from now on, the gift validator is named validator. And we calculate the validator's address with using utilities validator to address, and we provide the gift validator. So now we have the address that is going to be printed. And here we create, we are preparing the value. So we need the address, we need a datum, and we need the value. We always have to provide the datum. If you don't provide the datum, you won't be able to unlock it ever again so far, unless we change some fundamental part of the ledger. So you always need a datum and you always need a value. You cannot send an empty UTXO. So once we have our address, we're going to create a datum. Remember, as Lars said, said in the previous lesson, there are multiple ways of providing this datum in the transaction body or inline, etc. We're going to inline it because it's the most intuitive way of working with datum. So we're going to inline a datum. Here, we could just do data.void, and this will be fine. We don't need, this is going to be like a empty datum. It's going to be there. There is a datum, but it doesn't provide any useful information. And that will be fine because we're not using it. As you remember, we are just ignoring the datum completely. We don't care about the datum. But because plenty of people use the gift and burn validators to learn about Plutus, because these are the first ones, the simplest validators that you can build. When we try to consume it, when we try to consume the UTXO we just created, it's going to be lost in a sea of UTXOs that other people created and that we can consume because they are all inside the gift validator. So to be able to differentiate this UTXO, the one that we create, from the rest, I'm going to add this text, Kenya 2024, as datum. So then we can filter this datum, we can find it and filter, be sure that we are consuming the datum, the UTXO we just created. And as a value, let's count 1, 2, 3, 1, 2, 3. We're going to send 10 ADA. So we have the address, the datum, the value. Let's construct a transaction. We can use the new transaction function from Lucid. This new transaction creates an empty transaction that doesn't have anything. So we have to slowly add all the parameters we need of the transaction. So what we want to do in this transaction is we want to pay to a contract. We want to send money to a contract. And for that, we need the contract address, and we need the datum and the value that we want to send. We already calculated all that. Then we wrap that up, and we have a raw unsigned transaction ready to go. What we need to do now is to sign the transaction. If we try to send it, let's think about this. we said that anyone can send a UTXO to the gift validate to any validator. So a validator is not going to check that we can sign, that if it's signed or if it's not signed, whatever. So what do we need to sign? What someone needs to sign? Because as we already said before, to be able to create a UTXO, you have to consume another UTXO. And in this case, you have to consume the UTXO in your wallet, in this case, Alice's wallet, to be able to send money to the validator. So Alice has to sign the transaction so the UTXO in Alice's wallet can be consumed. And that's what we do right here. We sign the transaction, and then once we complete it, we have like our transaction already signed and ready to go. And all we need to do now is to submit it to the blockchain. Once we submit it, we're going to print in the console the transaction ID that then we can use to check a couple of times. I mean, we don't need it because we have our scripts, but we can use the Explorer to check how the transaction is going. So as you can see, it's 40 lines of code. It's not much, but it's enough to create a transaction. It's enough to produce a change in the blockchain. So let's run the script and lock the off-chain, log ADA in gift or born validator. And if we run this, we have an error because undefined cannot read properties of undefined. Let's see, gift _ born 42. This is no, this is fine. Let's see, where did I mess up? Oh, right. Let's see. It's because I'm trying to run this and I haven't written the born validator yet. So let's run this again. There you go. We have the validator's address, so we can just go to the validator and see all the UTXO that contains. And we also have the transaction ID that if we go to Cardano Scan and search for it, it's not going to be there because it takes some time for Cardano Scan to pick it up. But we can run the script off-chain that is check gift or born validator. We have a script for everything. So in the check gift or born validator assets, we do the same as before. This is repetitive, and that's good because you don't have to like once you understand it, like half of the script is always the same. And so we parse the Bluetooth JSON, we prepare the gift validator, we comment this because we don't have born validator. So this is the same as before, but then now instead of creating a transaction, blah, 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 all we do is to calculate the validator address and check the UTXOs at this validator address. And like we just print it. So if we run this, run off-chain, check gift or validator, and we run this again. I didn't save. Always save. There you go. So we have as you can see, a bunch of UTXOs. Actually, there's more in the gift validator. There's more UTXOs, but in these are there's like a cap of 5, max 5 or max 7 on Lucid. But one of these is our UTXO. So if we go back now, if we refresh this, we should have, or not, still. Oh, because we're in mainnet. Of course. Let's paste it again. There you go. So we have 6 confirmations. This is the transaction we just created. Our address from Alice spent 10 ADA plus the fees that you need to pay to the nodes, and the validator address received 10 ADA. And if we go to the validator address, you will see that we have 34 ADA in total with 154 transactions. And 3 minutes ago, Alice was the one that created this transaction. Actually, if we go to this transaction and where we just were, and we go to, this is the summary, but if we go to UTXOs, we see that we consume a UTXO from Alice, and we generated a UTXO both. We generated one UTXO sitting at the address of the validator, and one with the change 989 ADA to Alice. And if we, this is 3 minutes ago. Yeah, I think this is the correct one. And we can check actually, if we inspect the datum, we have these bytes that look like they don't do anything, but if we take any conversion tool, we see that this hexadecimal means Kenya 2024. So this is our UTXO. Okay, so let's consume this UTXO. Now Bob needs to consume. This is so big. Everybody can see if I zoom out a bit. So let me know. So we can, if we run script off-chain check wallet. Now Alice has less ADA, but it still has one UTXO, but with a little bit of less ADA. And Bob doesn't have anything, doesn't have any amount of asset in this address. But now Bob wants to consume the validator, wants to unlock the gift. So for Bob to be able to pay the fees, we're going to send some money to Bob.
By the way, if you want more screen real estate, there's a Visual Studio Code extension that I've installed. It's called Auto Hide, and that maybe you can try it to install it. Then when you click into your editor, the side stuff disappears.
Auto Hide.
Yes, Auto Hide. I think in 2 words. Yeah, the first one. I think now if you click into your code editor.
Oh, beautiful. Thank you. But still I can, okay, yes. And if I move away.
I mean, you can get it back when you click on one of the icons on the left, of course. I mean, if you want to see your Explorer.
Right. Awesome. Thank you, Lars. So we have a bit more space. Awesome. So I'm going to finish the round trip, and then we're going to slow down and to see the details. So now I want to unlock. So let's remove this. Let's remove this. Now, I want to unlock ADA from gift. As I just said before, we need Bob needs some money. Always needs some money, Bob. And we're going to send 5 ADA just so we don't we can like see the difference easily. We can spot Bob's UTXOs from the rest. No, how was it? And now Bob, that used to have 0 UTXOs, should have 1 with 5 ADA. So, Mr. Bob wants to consume wants to consume the UTXO we just sent to the gift validator. So we're going to load Bob Pokey hash, and we're going to select the Bob wallet as the current wallet of Lucid. Then, same as before, we get the Bluetooth JSON, and we ignore this one. And we create the gift validator, same as before. And this is I'm going to comment this. And we rename the gift validator to validator to avoid repeating ourselves and changing everything. So now, same as before, we prepare values. It's a bit different this time. We do have to do the same as before. We do have to calculate the gift validator address. We do have to get UTXOs of the validator. In this time, we want the UTXOs of the validator because we want to consume one of them. And because we were not interested in all of them, just the specific one that we created, we're going to filter. Actually, when we're going to use this find function, this find function is going to check for each UTXO the datum of the UTXO, and it's going to see if the datum is equal to this Kenya 2024 turned to hexadecimal. If that's the case, it's going to return the UTXO we just created. If like we forgot to create it, or someone already consumed what we were talking, it's going to return undefined. So if we cannot find the UTXO, we just console log, hey, we couldn't find the UTXO, and exit and finish the script. But if we did find the UTXO, we're going to print the UTXO to be consumed. We want to see what we're going to consume. And then we have to create a transaction. But this time the transaction is not to send to the validator, but to consume from a validator. So we create a new transaction as before, but here, instead of saying log here, instead of saying paying to contract, we say collect from some UTXOs. We are not sending money to a contract address, but we are trying to consume UTXOs. So we have to provide a list of UTXOs. In our case, we just have one, so we just create a singleton list with the UTXO we are interested in. And we provide this data that void as redeemer. In this case, I'm not sure if Lars already mentioned it, but the redeemer matters when you're trying to consume from the, yes, you already said. consume from the validator. So before we provided the datum because we were creating the UTXO in the validator. But then when we consume it, we need to provide the redeemer that is kind of the key to unlock the assets. In our case, our validator is keyless because we are just not checking anything. So there's nothing that we need to send that we need to provide specifically. So we're just going to provide the standard void datum because we never checked for it. So
And
we're going
normally,
to
and sometimes, I mean, depending on how the datum was attached, you probably would now have to do something in Lucid to also give the datum, or is that already included in the UTXO? Probably it's already in the UTXO, right? You don't have to worry about that in Lucid.
exactly in Lucid already. I mean, here when as Lars says here, when we provide this datum, we said that it was inline. So the datum is already on the blockchain. It's already there. And when we collect from without indicating a datum, Lucid assumes there is an inline datum.
No, I thought, I mean, I'm not sure. I mean, we will see that when with your line 34, when it prints the UTXO. It could be that Lucid automatically resolves datums if it can. So if the method, if it's not inline, but if the datum is on the blockchain but not inline, I wonder whether in that case it will also work automatically. But doesn't matter. But
yeah, I remember to have I provided datum somewhere in the past, but I don't remember if I checked with.
Okay, it's fine. But in this case, at least when we used inline, when we created, I mean, when we locked it, then now you don't have to do anything and it just works, right?
Yeah.
Automatically. Okay. Great.
Sorry.
Yes.
Sorry, Robertino. I just got another problem trying to find the Bluetooth.json. I don't know if because it is in the GitHub repository. I don't know how to
Yes.
Did you
No
do
problem.
icon build?
Yes.
Oh, okay. Yes, I just missed that.
Did you write this file, Giftborn? Did you write this validator?
Yes, I did.
Awesome. So if you save and run icon build, you should have it.
Okay, thank you very much.
No problem. Maybe I'm going too fast, but actually I wanted to go over. I mean, the interesting part is later. So this is a bit boring, and the off-chain code is the off-chain code can be written in many different ways depending on your language preference and your package and library preference. So we picked Lucid because it's easy for most people, because most people already know JavaScript and TypeScript, and it's pretty succinct. But this can be written in many different ways, and it's not really as crucial as doing a proper validator. But still, anyone, let me know if you have any doubts or whatever. I can slow down.
One nice thing about Lucid, I mean, you mentioned that before, is that because it's TypeScript, I mean, now we run it on the back end, but that you could also do it in the browser. So then if you know Lucid, then you can do both. The other alternatives normally are either for the back end or for the browser.
Exactly.
And that, I mean, that also depends on your setup. I don't know how most projects do it. I mean, the company I'm involved in, we have basically this off-chain code in the back end, and then the front end only, I mean, does like requests to the back end to interact with the blockchain indirectly. But I mean, others also do everything in the browser. So that's always, I mean, that depends on your specific project. But the nice thing about Lucid is that you can use it on both sides. And Lucid also has these nice abstractions. I mean, Robertino now did this wallet from private key thing. But if you are in the browser, you just do something else. I forgot the syntax, but basically connect to browser wallet, and then everything else is the same. So basically that line would change if you were in the browser. Instead of loading this private key from file and setting the wallet up with that, you would connect to your browser plugin, to Eternal or Nami or something. But then the rest, like the building of the transaction and so on, would be exactly the same. So that's very nice about Lucid as well.
Yeah, and we can do a front end from like eventually. I mean, I don't know if like how complex we are going to go in this course, but we do have a stable coin that it runs pretty much entirely in the front end. So that's also like we could showcase that as well if we reach that far, or maybe we could do something more like the vesting front end for the vesting or something like that.
Yes, definitely.
So let's keep going. So we create a new transaction and we want to collect from this UTXO. And this is a bit counterintuitive for people that come from maybe Web 2 or other other technologies, is that when we created the UTXO in the address, we didn't provide the actual validator because we didn't have to. We just need to log something in the address, and the blockchain doesn't need to have the actual bytecodes that are used to derive that address. The address is already there. So when we send the money, we don't provide the validator in this specific case. But when we want to consume it, we need to provide the actual validator, not only the address. We need to provide the validator to the node, so the node can say, okay, let's check if if the validator really allows you to spend, to consume this UTXO. So that's why now we have to attach the spending validator to the transaction. We have to say, okay, to the blockchain, which is actually to one of the nodes of the blockchain, we say, okay, I want to collect this UTXO. This is the redeemer, and this is the validator. So the node is going to hash the validator, is going to check that that validator is actually the one that's the one that generates the address that you want to collect from, and then is going to check if that's if the validator allows you to do that. So that's why we want to attach the spending validator to when we consume it. Recently, relatively recently, we have a new way of doing this, which we can put the validator on chain as like before consuming anything, just like the actual code of the validator, and then we can reference it. We can reference the script, so then we don't have to attach the spending validator every time we want to consume from the UTXO. We'll see that in the future lesson, but for now we're going to do like the simple way. We just attach the spending validator when we want to consume it. If we don't attach, if we don't do this, we'll just say, hey, we just want to collect here. The node, the blockchain is not going to allow us to do that because it has no way to check if the validator actually returns true. So we have this transaction, and this is pretty much the only thing that differs. Everything else is the same. So we sign the transaction and we submit the transaction. So now we can do first we're going to run script off chain check check gift 49 6B. I think this was the one that we just created. This is what we just translated in the hash. So we're going to consume that one. And we're going to run script off-chain unlock ADA from gift or born validator. This is the script we just went over it. So if we run this, we see that the UTXO to be consumed is this one. As you can see, the datum right here is the same as we just saw before. They was in the script. So we want to consume this UTXO, and this is the transaction that it appears to be that it was accepted. At least it didn't fail. And if we take a look at the transaction, we cannot find it because it takes some time, but we can check Bob's wallet. So now Bob should have 10 more ADA. Let's go to off-chain, check wallets. Bob address now has, it used to have only 5 ADA because we sent 5 ADA, but now it has 14.8 ADA. So it's 15, it's the 10 ADA that consumed, that got from the UTXO, plus the 5 ADA that Bob had before, minus the fees that Bob had to pay to be able to consume the UTXO from the validator. So this was the whole round trip from like pretty much for all spending validators is the same. Someone logs ADA in the address, someone else tries to consume it and has to provide the appropriate data that can be a redeemer, the validator, datum, depending on how it was created the first time. And that's it. As you can see, the validator itself is not an active participant, it's a passive participant. It's the creation of the transaction, the Alice and Bob that are active participants and want to use the validator. Do we have any questions now? Let's see if we have this already.
No, in the chat.
What's in the chat?
No.
So as you can see, Bob consumed 10 from the address and got 9.8. So now, maybe this was a bit overwhelming if it's your first time, but the cool thing is that it's from now on is pretty much the same from the rest of the course. Like the only thing that gets slightly complicated is this part. When we create transactions, it can be a bit more complicated. When we prepare the values, it can be a bit more complicated. But this part is pretty much always the same. Like get some key to be able to sign some way or another, get the values, create the transaction, forget about it. So let's see, now we can go back to the gift and burn. And
should we have a break at some point? Or do we...
Yeah.
sorry, yes, of course. I didn't realize that so much time passed.
So much enthusiasm. It's great.
Okay, yes. Let's have a short break until 2 p.m. maybe, because I think we have, and then we go until 3.
Yeah, sounds good.
Okay. So 15 minutes until o'clock.
Okay.
Okay, see
Thank
you
you,
everyone.
Martina. Thank you.
Okay. Should we continue?
Okay.
Awesome. Adrian, everything working on your side?
Yes, but I still have some problems.
Right.
But I think these are on my side, so I think I will watch the video again, and at the end of of this of this lecture, and I will get all the information from that.
Sure, sure. Perfect. Okay. Anybody else has any questions? Kennedy, Dennis, Timothy? Okay. So I'm going to slow down a bit. We covered a lot of new concepts and a lot of code. So I think we should like step it down a bit and just look at the Aiken code for a bit and explore it and explore the documentation, etc. So before moving to that, let's see the Born validator. So as likely you can imagine, the Born validator, I have a snippet here that just creates a new validator for me because I'm lazy. And I can just Born validator. And the Born validator is the same as the GIF validator, but returns false. And in this case, there are a couple of new things here. So one is that we have this colon data twice in colon script context. This is how we indicate types in Aiken with the colon and then the name of the type. All the types start with uppercase and variables start with lowercase. And this data type, we already talked about this actually when we saw the Plutus blueprint. This data type represents any Plutus data. So it can be an integer, it can be a byte array, it can be anything that can be represented in Plutus data. So it's like sort of like the any type of TypeScript. It doesn't reduce much the options. But in the context here, we have this script context type. So this script context type is more interesting. Now the underscore CTX variable can only be a value of type script context. And we're going to explore a bit what does it mean for the script context. We have this error, this, hey, did you forget to import it? Yes, I didn't import, so I can just use the server, that communicates through the language server protocol that can import it for me. So if I click here, if I accept the suggestion, we see that how we can import things in Aiken. We use the use keyword, and then the name of the module, and finally dots, and inside the brackets, we import specific things. Else, we can just do like this and import the whole module. And so in our case, we're going to import the script context from Aiken/transaction. So this is virtually the same as the GIF validator, but with the one caveat that it always returns false. That means that it doesn't matter what do I provide to this validator, it will always return, it will always reject the transaction. When I send money to the validator, the UTXO is going to be created in the Born validator's address. But when I try to consume the UTXO from the Born validator, I'm not going to be able to do it. It doesn't matter where do I do. So you have to be really careful because if you send something to this address, there's no way you're going to get it back. But we're not going to go over the whole process of sending and consuming and blah, 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 because it's exactly the same as the gift validator, with the caveat that when Bob tries to consume the UTXO, it's going to fail because no one can consume from the validator. So you can do that in your own time. Now, we want to create a new validator that's a bit more complex. But for that, we have to explore a bit more the Aiken, everything, the Aiken language and the Aiken standard library, because we don't know what we can and we cannot do, etc. So one thing you could do is to go online to the standard library, to the Aiken documentation, and then you have a link to the docs. But you can do it in your own browser, because you can do Aiken docs, and this is going to generate the documentation for Aiken, and not only the documentation for the standard library, but also if you happen to like documents, you can use this is a comment. This is a comment, and this, oh my God, this is documented. So if you use 2 backslashes, you comment stuff in your code. But if you use 3 backslashes, you can create documentation that is going to be generated for your code specifically in the browser, in the files that we're going to see right now. So we generated this documentation, and now you have to have a way to open this, right? So one option is to just use Firefox or whatever this documentation is right here in the docs folder. And as you can see, we have this index.html. So, I mean, you can just open in your browser. We actually provide, we added in the Docker container, if we check the alias, we added this server. It should be serve docs, that it runs a Python server and opens the docs, that opens this docs folder. So we're going to use that because it's quicker, but just know that you don't need to be inside the container to be able to do this. You can do it in your own machine. But serve docs, opening browser, and final phone. Let's see. Cryptocurrency. Oh, right. Small issue. No problem. The error is because when I created this, I was in a different repository. Haskell cryptocurrency. So this one is Workspaces Cardano Dev 2024. Like this. Cardano Dev 2024 example.
Yes.
Awesome. So we are going to change this. Someone is going to change this and push the changes. So you can do it yourself. Now we should run awesome. So we have our documentation. And let's see. So we have 3 important modules that we want to talk about, 3 important standard documentations. And we have the docs. Here we have the README file of the repository. So as you can see, we have dev container configuration before using this thing we wrote. But what the interesting part, let me zoom in a bit. The interesting part is that here in the top right, we have the preludes, we have built-ins, and we have the standard library. So the prelude is same as Haskell. It's that there's a subset of functions from the standard library that are imported automatically, that you don't have to import manually. It's already pre-imported for you. The built-ins are functions that are part of Plutus core. Usually, you don't have to deal with built-ins directly, because it's a more low level, and for most use cases, there's no need to reach for this level of control. So usually you're just going to work with the Prelude and the standard library. If you go to Prelude, we have, for example, the Boolean type. The Boolean type can be false, true, same as Haskell. We have byte array, data, fuzzer, etc. Int, lists, optional value. Here we have, I already scrolled away from it. Here we have an optional value that is the same as, it works same as maybe. Some A is just A and none is nothing. And you can like browse around and see, for example, we have ordering, same as Haskell, string, void, and we have a bunch of functions that are already like flip. We have used flip, I believe. In Haskell, we have the identity function and the not that returns the opposite of a Boolean. So it's really small library, as you can see. Like you can just read it in a couple of minutes. The cool one is the standard library. If we go here, this standard library gives us all the information pretty much that we need to write the all the validators that we're going to need in this course. And of course, if you start to build your own libraries, that you could use like the standard library as an entry point, and then have like build more build functions that solve problems that you are having right now. That if we do it faster enough, maybe we can do a couple. So the Aiken standard library contains all these modules: byte array, seaboard, dictionary, hash, int, interval, etc. But we can search same as with Haskell right here. So the first new thing that we saw was data. I think it's the data. Data is an opaque. So redeemer is the same as data. Type alias, blah blah blah. Data is opaque because it's user defined. It's not script. So I think it's better to go to the validator. There you go. So we have data. There's this opaque value that we can use like anywhere. And the new value that we have is this script context. Script code, Lars said in the previous lesson that data can be anything and it's defined by ourselves. And redeemer can be anything and it's also defined by ourselves. But the script context cannot, like the third parameter cannot be anything. It has to be a script context. And the script context is generated, it has to contain a specific set of values that between all of these values, it describes the transaction as a whole. So it describes everything that goes into the transaction, everything that goes out from the transaction, the time range, if something is minted or burned, everything is described inside this script context. So let's take a look at this script context. Script context. Inside the script context, we have 2 fields. This is same as Haskell. We have the type, we have the value constructor, and inside the script context, we have the transaction of type transaction, and we have purpose of type script purpose. Here we have the script purpose. It characterizes the kind of script. In our case, we have worked only with spending validators. So the script purpose that we have been utilizing was the spend purpose. We want to spend a UTXO, but as you can see, we can also mint. We can this is what you do when you want to get NFTs or tokens, and we can do other withdraw and publish other stuff with credentials that we discuss later. For now, what we really care, and most of the time we're going to work, is the spend and mint purposes. And here's the transaction type. That this is the meat of the of the information that you have available to work with in your validator. So each transaction can know about its own context, and that's it. Like Lars already explained, that Ethereum has access to the whole blockchain, and that's great because you have access to everything, but that also sucks because anything can change at any time and it's out of your control. And if it changes while you build and submit your transaction, it's going to fail, and you have to pay fees, blah, 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 blah. In the Cardano case, we only have access to our transaction and the context of our transaction. And that means that if we are the only ones that are consuming the UTXOs, and that no one can do anything to change what the outcome of our transaction, the only thing that someone could do that could affect our transaction is that they consume a UTXO that we wanted to consume, but in that case, the transaction just fails without consuming any fees, and nothing is lost, and you can just rebuild the transaction and run it again as many times as you want with new UTXOs. So we have this transaction, and the transaction contains a list of inputs, all the UTXOs that are being consumed by this transaction, a list of reference inputs. We can read from other inputs. We can read values in other inputs without consuming them. We have a list of outputs, all the UTXOs that we want to generate in our transaction. The fee that we want to pay, that we need to pay. We have the mint value, that the values that we want to, the tokens or NFTs that we are creating or destroying. And we have other stuff like certificates with ROC that we'll talk about later. We have the validity range. Validity range is the time frame within which the transaction is valid. If you can just avoid, your smart contract can just not check, like the ones that we have right here. Our current gift and burn contracts don't care about the transaction range. So we can consume UTXOs from these validators at any point in time. But we can, by using this validity range, we can constrain the time. For example, you can only use this validator, you can only consume from this validator in 2020, in December 30, like the 30th of December of 2025, something like that. And from there to like 2 of February of 2026. And we can create this range of time where the smart contract is accepts the transaction, and in that case we're going to check it against the validity range of this transaction, the validity range of the transaction itself. Then we have the extra signatories, and the type seems a bit daunting, but it's just only this verification key is what we had from Alice and Bob. But this verification key, where we need to hash it using this specific algorithm, but that's not important. So we have a hash of the verification key, and that's how we identify who signed the transaction. And because multiple people can sign the transaction, we have a list of these hashes of verification keys. So this verification key will be the public, the private key, and this Blake, and this hash will be the hash. Sorry, the public key, and the hash will be the hash of the public key. So this is how we check who signed and who didn't. So we have we can access inside our smart contract who signed the smart contract. That's also something we can take into account to create the logic of a smart contract. And finally, we get a dictionary of redeemers. The redeemers of all the redeemers we provide in the transaction, and datums of all the UTXOs of the transaction that we want to consume and generate of the transaction. So the important thing is that the transaction itself is pure, and the validator itself is pure, and because of that, it needs to access this information as an input. So this is all the information the validator needs to work, and this information is provided inside this context, this script context. This is how we can do more interesting stuff and not just boring stuff. So I thought about doing the 42 example. Actually, we have everything. Yeah, let's do it. Let's do that. So we're going to create a new validator now. We're not going to use the script context yet. So let's create a new validator. The validator name is going to be 42. And this validator is going to check that the redeemer, these are, we're going to name it redeemer. This redeemer has to be equals to 42. The thing is that if we use it like this, we can see that we have an error. The agent says, hey, I'm inferring the following type of data, but I found an expression with a different type. So here, this expression is comparing redeemer to an integer, but here I'm saying that redeemer has a type of data. So what I need to do here is just change these to, just listen to the compiler. Always follow what the compiler says. And I changed the type from this generic data to this redeemer int. Now, I cannot provide this data, that void that I did in the off-chain code, because I need to provide an actual integer as redeemer. This 42 type, 42 validator, now it doesn't return always, doesn't unlock UTXO always, and it doesn't reject it always, only when we provide the redeemer of value 42. Let's check it out. Let's try it. So we're going to create a new shell, and because we want to use this validator, we need to compile it first. So a can build. There you go. We built the compiler, and if we go to this Plutus.json, we'll see that somewhere around here. Now we have this new int data type of type integer, and 42. There you go. And here inside the list of the validators, we have the 42 validator that takes as datum this generic _d of type data, but as redeemer, now it's named redeemer without the underscore because I'm using it, and if it's of type int. And here we have the compile code. So we can start using it. Let's see, let's log Ada. I think I already log Ada. Yeah. Let's log Ada in the 42 validator. So, same as before, we read the private key from Alice, create the wallet, we read the Plutus JSON, but now when we create the validator, this is a spending validator Plutus v2, but now we chose the 42 validator. So now we're using a different one, and we, same as before, to prepare the values, we create the validator address, and we create the datum, as we see right here. The datum is still, we don't care about it, we don't use it, so we can do anything with it. And in our case, because we don't care about it, we'll do the same trick of populating it with a string that we already know to easily filter out and make sure that we are consuming the one we want. We, as value, we provide the same value as always. Actually, we could just do something different. And we pay the transaction, new transaction, pay to contract. As I said before, we provide the redeemer when we consume from a validator, not when we send to a validator. So this is same as for the gift and born validators. We just provide the validator address, any random datum we want, and the value we want to log. We signed and complete. So if we run the script, log Ada in 42. There you go, we logged. And if we run script off chain, check 42 validator, still empty. It's the same address, test one WRJ, yes. So it's the same address, but the transaction hasn't been processed yet. Let's try again. Let's see, transaction submitted. Any questions so far? So this time, oh, there you go. So now we have two. For some reason, maybe someone just sent it at the same time. So now the validator, the 42 validator has two different UTXOs. We have some validator that has 5 ADA, and with some random datum. And we have the one that has 12 ADA that has this 49 CB hex that we know that it means, but because I already checked before, it means Kenya 2024. So now we have the UTXO there. This part was same as before, boring, but let's see how we can consume. Let's unlock ADA from the 42 validator. So Bob wants to unlock the ADA. So we load Bob's wallet, we load the validator, we calculate the address. This is all the same as we did before. We find the UTXO, we get all the UTXO. We find the one that we actually care about because it has this datum containing the Kenya 2024 text. If we have nothing, we just return, we just exit, and else we want to consume this, and this is the cool part. So now I'm going to try to collect from this UTXO in 3 different ways. First, I'm going to try to collect this UTXO from the 42, providing some value that is not an integer. So this should fail because it's not even the same type. Let's try that. So run script, off-chain, unlock ADA from 42 validator. As you can see, we found the UTXO that we wanted to consume. It was exactly as we did, the one that with 12 ADA and the correct datum. But we had we failed to deserialize the Bluetooth data because we tried to deserialize this data as an integer, but it wasn't an integer. So the validator rejected the transaction. But we can try with the correct data. In this case, we are sending the redeemer of value 33. And in this time, we have the correct data, but the wrong value. It should be equal to 42. So if we run it again, we found it, and they provide Bluetooth code called error. So the data deserialized correctly. We did have an integer, but the validator itself called error because it didn't satisfy the logic of the contract. Finally, if we provide the correct value of the correct type, we should be able to consume this, and we are able to consume this. Amazing. So if we now check the 42 validator assets, we see that there's only this 50 random one, and the one that we had before is gone. And if we check Bob's wallet, we see that Bob now has 26 ADA. So it has a single UTXO of 26 ADA. It's still a single UTXO. As you can see, both Bob and Alice always have a single UTXO because they have a single, they consume their UTXO to pay the fees and then generate a new UTXO with the added amount or reduced amount in their own wallets again. So we are always consuming one UTXO and generating a new UTXO, but the value itself, the value contained in the UTXO is changing. So this is a less boring, I will say, still boring, but less boring validator. And we did as a whole round trip. And as you can see, we changed the logic of the validator, but The only thing that really changes was a single line of code that provided the correct redeemer. So we still have time. I think it will be cool if I'm not sure if we have any questions, but I was thinking that maybe I could like do code live the vesting validator, or maybe because to explore a bit the types and stuff like that, or maybe if someone has any questions, we can go back and like revisit something. I think it will be a nice homework to do. Validator that checks datum is same as really. This is the homework. If Lars is fine with it. So the homework is to write the next, I will argue, next complexity level that will be using a validator and of chain code. So we have a way to compare if the redeemer is the same as some hard-coded value. So the homework is, now I'm going to provide some value as datum and some value as redeemer, and I want to make sure that that datum is equal to the redeemer. And if in that case, you can unlock the value, else you cannot. So I think that's appropriate level of complexity based on what we covered so far. So if anyone has any questions, we can slow down, we can explore things in specific scenarios or specific technologies, more Aiken, more Lucid. Else I can start, maybe, I'm not sure it's enough time, but I could try to quickly code a more complex vesting validator. Anyone has any questions?
Yes, I have a question.
Yeah.
Can you walk through the difference between the redeemer and the datum?
Yeah, for sure. So there are a couple of key differences. The datum is something that is conceptually, is something that is part of the UTXO that you want to create or consume. So the datum and the UTXO go together. On the other hand, the redeemer is something that comes with the transaction. The redeemer is something that you provide to be able to consume the UTXO. So you can think of that conceptually, independently of how it's provided, how the datum is provided. The redeemer is always provided by the consumer, because when you create the transaction, there's no need to unlock the transaction you are creating right now. So the redeemer is only used to unlock UTXOs. But the datum is something that it sits conceptually, it sits with the UTXO. It's something you can save data. For example, you can save state in the UTXO inside this datum. And many use cases, many real world applications use this datum as something that stores information that then can be used by the validator to be For example, let me think. For example, you can save here in the datum, you can say list of people that can unlock, that can consume this UTXO. So when you create the UTXO in the validator, you create it providing a list of all the people that can unlock this UTXO. And then in the redeemer, when someone wants to consume this, it's going to, in the redeemer, you can ask for the person to sign it or provide some value in the redeemer. Actually, you don't need the redeemer in that case because you have all the signatures in the script context. But this is for example, you can actually, we can call it right now if you want. We can save a list of keys that can unlock the UTXO in the datum as a state, as part of the UTXO, and then use the check if someone from that list signed that transaction in the script context. And then once you have that, you can create many different UTXOs with different values inside this data. So you can create this generic DApp that allows you to lock money that only your family can consume, for example. So you, inside this datum, you put all the hashes of all the public hashes of your family members, and you create that UTXO. And then someone else creates another UTXO with their own family members. So that's the state that I'm referring to. That's the extra information that you're providing in this datum that is attached to the UTXO. And then when some family member wants to consume, is going to sign the transaction, and you're going to be able to compare from this UTXO, this data that is inside the datum, if it's inside that list is contains someone that signed the transaction. So if you consume if you try to consume in the same validator, there are two UTXOs, and you try to consume the UTXO of that generated by your family member, you will be able to consume it because the datum contains your key. But if you try to consume in the same validator another UTXO from another person that has a family member, that you're not a family member, you won't be able to consume it. So it's the same validator, but now some UTXOs you will be able to consume and some not, because the data that is stored with the UTXO, the datum, is different. Does it make sense? That's one of the key difference and use cases. Store information in the datum, and the redeemer in the example I just said is not necessary because you can just use the script context. But here in the datum, you can say, in the datum, I'm going to write some secret password that is not how you signed, and then you can provide as redeemer the same secret password and check that the datum the redeemer are equal, which is the homework. So that's another use case that using both. But that didn't make sense. Can you tell me if there's some specific thing that didn't make sense?
That was a clear explanation, I think. So I think, for example, if we have a redeemer, this is something like when we are calling the transaction from TypeScript, and we are providing the redeemer, right? And when we are well, the UTXO has attached the datum, right, as you explained?
Yes, exactly. So you cannot change a datum in that with a UTXO's datum. A
Okay.
UTXO has a datum and that's fixed. Once it's created, that's done. But you can choose the redeemer you use to consume that UTXO.
Okay. Okay. Thank you.
Awesome. No problem.
I just want to add that, I mean, I did say that the extended UTXO model is an extension because normally without smart contracts, the way it's validated whether you can consume a given UTXO is the transaction must be signed by the owner. I mean, one way to think of redeemers is that the redeemer is a generalization of the signature. So instead of having that the specific person has to sign the transaction, you can think of the redeemer as something like a signature that then unlocks the validator. But that is not always the case. And another use case or another thing people use redeemers for is to pick an action. So I mean, we will probably have like more interesting examples later. So sometimes there are different ways you can spend a UTXO. For example, in the context of a decentralized exchange, if a UTXO represents an order, so somebody wants to swap, I don't know, ADA for something else. So he locks some ADA there, and then the datum would maybe contain the price that he wants. I mean, what he wants in exchange. And then there might be, I mean, there can be two possible actions. I mean, what can happen with the UTXO? One would be that somebody actually pays the price and then gets the ADA. And another action could be that the original, I mean, the creator of the order wants to cancel it. I mean, this is a silly example because there you wouldn't really need the redeemer. But I mean, you could use the redeemer that the redeemer has two values, something like fill and cancel. And then if you want to fill the order, you use the fill redeemer, and if you want to cancel, use the cancel redeemer. I mean, in this specific example, it wouldn't be necessary, but I mean, in more complicated examples, that's often what people do, so that the redeemer, instead of thinking of it like a key, you can also think of it like picking an action. So UTXO allows like different modes or ways of spending it, and then the redeemer would pick one of those. But as Robertino said, I mean, the main point is that the datum is created by the person that placed the UTXO there, and it's attached to the output, and the redeemer is picked by the person that wants to spend it. So it's different actors, basically. The creator of the UTXO chooses the datum, and the spender of the UTXO chooses the redeemer. And then what exactly happens, I mean, that depends on the validator.
Yeah. So I wrote some code that represents what Lars says. So you can have two different logics here, and that each run depending of what the action has to be. So if you want to delete, you run a specific validator, and else you run a different logic. Oh, too much. So we have 12 minutes. Not sure if I should start with a more complex one, or if someone has questions, we can go over something else.
I have a question.
Yeah.
So, like I didn't quite get how you set the script context.
Yes.
For in your validator codes. Maybe you can.
Yeah, for sure. So the thing with, let's see, script context. So the transaction itself, if we only had the data in the redeemer, we couldn't do much. With only datum and redeemer, we have a pretty dumb smart contract, because you cannot take into account a bunch of things that we care about, that it's important to it. So to add those things, we have this script context. In the script context, the only thing it provides is the context of the transaction that you are trying to create right now. So if you are trying to consume two different validators in a transaction, the script context is going to contain them and all the inputs and all the outputs, and that changes transaction from transaction to transaction, even if you're trying to consume from the same validator, because you cannot have the same UTXO twice, and the time keeps going, so you cannot have like the same time always, etc., etc. So this script context is extra information that is not in the datum and in the redeemer. Now, this extra information could be anything, but it was decided by really smart people that what we need to have inside this script context are at this transaction and the purpose. So we already talked about the purpose a bit. The purpose is just like a couple of options that you can do. Everything we said so far is part of the spend transaction purpose. So we want to consume UTXOs. But what I'm referring to with the context of the transaction, what you need to do some more interesting stuff, is everything inside the transaction type. So if we only had the datum and the redeemer, you could do very basic things, like make sure the datum is smaller than the redeemer, or equal, or they are different, and a couple more things, and you don't have many more things you can do. But with the transaction, you have this extra information that it's supposed to represent everything that you care about the transaction. You don't really care about like who's the node that is validating it. You don't care about what's the version of the off-chain code that sent the transaction. Those things are not important for to make the decision if the UTXO can or cannot be consumed. What it does matter is what are the inputs that I can consume in this transaction, because it's very important to know what you are consuming from where. If you are the information that you get from the reference inputs as well, because you can use, for example, you can use the information from other inputs that you're not consuming to make decisions to consume inputs to other inputs, different inputs. So this could be like an oracle that says, hey, the price of the US dollar, of ADA in US dollars is that much. So you can, if the input, you can consume this input if ADA is over $1, for example. Then you have the outputs. The transaction needs to know which outputs you are creating, because you can restrict validation according to that. Else, you will be able to send those outputs anywhere. And for example, there are plenty of use cases that rely on checking that the outputs you are creating go to a certain script or contains a certain amount of tokens. So for example, if you are creating an NFT, the NFT can be only one. And if you are consuming, but that's an input. Let's see, outputs. If you are trying to update a value in a UTXO that is sitting on a smart contract, on a validator, you are consuming the UTXO from the validator. So if you cannot check that you are recreating the output with the same amount but updated datum, for example, it's useless. I mean, I could just take the money and run away. So I'm going to write the validator in a way that I can check that you are sending the money again, the same amount of money that you consume from the validator, you are sending again. So the only thing that you can actually do is modify the datum, for example. That's pretty much how you can build an oracle, that we have an example for that later on. You want to know if you are minting values, as I was saying before, like if you are minting an NFT, you want to make sure that you are minting just one of these specific token asset. If you don't have this minting in your transaction, there's no way that you can be sure that you're creating an NFT or 10 million tokens. So all this the point is, the transaction has all the information that is critical for the developer of validators to have on hand to be able to write pretty much any logic that it needs. No more, no less. I mean, you could argue we should add something else, or you should remove. And actually, if you see how Plutus evolves from V1 to V2 to V3, you see that more things are as the blockchain evolves, more values, more concepts are added to this script context. So before we didn't have reference inputs, and now we do. So before you needed to consume an input to be able to read it, and now there's no need. So this information is still evolving, and it will keep evolving through the time. But what you really need to understand is that this is the concept of the transaction you are creating right now. Like you are trying to, the validator is validating a single specific transaction. So this information is relevant to be able to write the logic of that validator, and that's it. It will change. It will likely change through the time, but it's just pretty much, it's going to be, I believe it's going to be only add. I mean, we're going to add more options, but not reduce them or change them to maintain backwards compatibility. But that doesn't make sense. So with Redeemer and Datum, there's not enough information to write rich validators. So you need more. You need more information to be able to write dexes and stuff like that.
Thank you. It's you've explained it well.
Okay. So we ran out of time, and maybe I know make sure to do the homework, and actually if you can just change the when you send the transaction with your own validator, change this text to your name and send us the transaction ID, and that's enough to check if you actually completed the homework, the assignment. Let's see. Yes, and it's really short, the validator, so you can actually, yes, I'm not going to do it. But it's really short. I think you're going to make more changes in the off-chain code than in the actual validator. Do you have any questions, any requests? I think from now, I think this was the hardest lesson, I believe, because it's the first one and we introduce a bunch of new concepts and a bunch of new code. But then it's going to be like slower because we need to introduce small specific concepts, and we're going to develop the validators more slowly. So if you survive this lesson, it's going to get easier from now, I promise.
Do we already know what we do on Friday? Is it vesting and stuff like that?
I think we could do vesting like live, or if
we can still agree who does that, whether you want to or whether I should. But yeah, I think that's a good idea. Then we will, for the first time, see how the context is actually used, right?
yes. So far, yes, it will make maybe more sense once we work with it. Yeah.
Yes, and I think vesting is also really, I mean, it's the first realistic example of something that you could actually use and that is used in the wild in production. So that's nice. Then it's a bit more, I mean, not just a toy example, that's then something that actually is really useful.
Yeah. Yes, and we're going to go slower from now on.
Well, it was fine, I think. I mean, you demonstrated everything, and for example, Adrian definitely followed along, so it was possible to follow along. Very nice.
Awesome. Awesome. Okay. Awesome. So if we don't have any more questions, see you on Friday.
Yep. See you on Friday. Thanks,
Okay.
everyone.
Bye, everyone.
Thank you, Robertino. Thank you, everyone. Bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye-bye. Bye-bye.